Chung was at a conference in Minnesota, and I went there with my student Andreas, and then at one of the lunch breaks, we first sat together, had lunch, and then we took a little walk over the campus of Minnesota, and then we saw something shiny in the bushes. And so then Yeonchung went there and then picked it up, and it was an old lamp, and it was very dirty. So he took some cotton, and then he wanted to clean it up. And then smoke came out, and then all of a sudden a big genie appeared. And then the genie said, "Oh, thank you for liberating me out of this lamp. And you have 3 wishes. And since you are 3 people, so maybe 1 wish for each of you. So who wants to go first?" And then my student Andreas said, "I want to go first. I want to go first." "Okay, so you go first. What can I do for you?" And then he said, "Oh, I really would like to be in Hawaii on like a fast motor boat, and then having a nice girl next to me." And then poof, he disappeared. "So who wants to go next?" The genie said. And so John Chung said, I go next. "Okay, what do you want?" So he said, "Oh, really, I would like to be at Jeju Island with my wife and having a nice soju in my hand and just relax." So poof, he disappeared. So then the genie asked me, "So what can I do for you?" So I thought a little bit, and then I said, "I want them back by 2:00. So then the meeting continued. So, okay. Now, let's talk about the brain. So 5 applications. So let's talk about the brain first. I mentioned already that I like to apply all this, what I developed for brain tumor growth. So the brain, of course, is a very complex, complicated organ. And if you look at it from a geometric point of view, it has basically 2 distinct areas, which are called gray matter and white matter. Gray matter and white matter. And let's just say this is part of a skull, of a brain. So then the white matter are nerve fiber tracks which connect different areas of the brain. So there can be nerve fiber tracks going from one side, from back to front, or they can go left and right, or they can connect areas here, and there can be branching, etc., etc. So this would be then the white matter. And they connect different areas of gray matter, which is kind of between. So this would be then gray matter. And I'll show you pictures later where we can see this like in a medical image. Here it is just a sketch. But now if a tumor develops, maybe somewhere here, okay, then it is known that the tumor cells follow the white matter tracks to invade. So at a certain point the tumor becomes really aggressive, metastases form, and then individual tumor cells come out and they really move. They actively move through the brain. And so in this image, they would maybe move more this way and more this way, and maybe not so much this way. So they can also spread into the gray matter, but not so much. They prefer these highways which are laid out by the white matter tracks. Okay. Let's look at wolf. So the second application I have in mind has to do with wolf movement. And this is a typical Alberta problem or Canadian problem. So let's imagine this piece of the blackboard is a forest. And then in Canada, the oil companies, they cut through the forest and then they drill into the ground and let explosions into the ground. And they want to measure the resonance and then find oil. So what then happens is that a piece of forest is crisscrossed by a number of lines where they set down these explosions and then measure out a whole area of forest to find oil. And some of these could be roads, so maybe this is a bigger one, this is maybe a road, and then the others are the seismic lines. But still, this is an intact forest, so there are still a species in there, in particular wolf. And then the wolf, they can use these lines to walk on, right, and to spread out. So maybe, let me try to plot a little wolf here. Oh my goodness, It doesn't work. Okay. Yeah, that's good enough. So the wolf, they prefer to walk on the lines, but they also teeter off into the forest. But then they can increase their hunting success. So now it is all of a sudden it's easier to find prey, to find the deer, and then they can capture the deer and kill it. And so then the deer population goes down, and it all changes the whole ecosystem of the forest. So the similarities in these is the directed movement, right? So here the tumor cells, they move along these white matter tracks mostly, and the wolf, they move along these seismic lines mostly. They can also move into the forest, but they also like to be on these seismic lines. So what kind of data do we have for this? On the cell side, we can follow individual cells, cell movement. But here I'm a little bit cheating. So we cannot yet do individual cell movement imaging in a functional brain. So nobody lets me open brains and then put a microscope in there and look. But this can be done in brain-like tissues, right? So we can create tissues which have similar properties, put cells in there and observe them. So let's say brain-like tissues. And then for the wolf, on the wolf side, we have GPS collars. GPS collar data. So you can capture the wolf, you give them a GPS collar, you let them run again, and every 5 minutes you get a signal, and then you know exactly where the wolf is. Yeah, and then about the geometry of the brain. So we also need to know where are these brain fibers and how they are connected. And this is called diffusion tensor imaging, DTI. Which gives us information about the connectivity of these white matter fibers. And then here on the right hand side it's even easier, it's just maps, right? You just map out the forest area and you find all these seismic lines. And this gives you the geometry of your domain. Okay. So let's put this now into the framework of this transport equation modeling. Okay. So transport equations are useful in particular because for the transport equation we have a cell direction, right? We have this v, the cell velocity, and now we would like to relate it to the environment. So it is important if the velocity is in direction of the white matter fibers or perpendicular. So that's why transport equations are very, very useful here. And so I introduce a new variable for the environment, which I call q tilde of x and theta, where theta is a unit vector, Sm-1. And this is just a distribution of directions that occur in your environment. So basically on one of these lines here, you have a distribution of directions along this seismic line. But if in an intersection, maybe here, you have more directions which intersect. And so I just collect all directions which arise, and I call this the distribution q tilde. So distribution of directions. So then it should integrate to 1 and it should be non-negative. But it can be a measure, it doesn't have to be a smooth function. Okay. So, but we want to use the transport equation framework. Transport equation, so let me write it down again. Pt plus v times gradient p is minus mu p plus mu integral t of v prime pv prime dv prime. And what I like to do is to compare the movement of the cells v with the direction of the white matter theta. So I constantly have to kind of compare unit vectors, so directions here, and orientation vectors v. So it makes sense to lift this distribution q tilde onto the larger space v. So let me just write this down and then it's pretty clear what I do. So I introduce q of x v I want this to be q tilde of x v divided by the length of v, so just use a unit vector, because q tilde is only defined for unit vectors. And then I normalize it so that I get a probability density function. So then I normalize this integral v q tilde of x v divided by v dv. Okay? So then this q is a nice probability density function on the space V. And I do this only, then I only have to worry about this space V and can use it consistently for all the terms. Okay, so now we make a specific choice. We choose this kernel T of VV prime to be this distribution of directions. Okay, so then I should put an x here too. And this is a v. So T of VV prime, this is a probability to switch from V prime to V. And I say whenever an individual changes direction, it chooses a direction from the network. It chooses a direction which is present. Right? So if a wolf encounters a line, it's very likely to go on the line. Or if the cancer cell is on the white matter tracks, it's likely to continue on the white matter tracks. So the environment Q, this is used as the turning kernel in my transport equation. All right. So, and then the transport equation simplifies a bit, because now see, this Q does not depend on V prime, but here I integrate on V prime. Okay? So then I can take this Q even out of the integration. So let me write this down as well. Pt plus V times gradient P is, then we have minus mu P plus mu times Q times P bar, and then P bar is the integral of P over velocity dV prime. So we have this. Yeah, so a nice transport equation. I've written it down in one of my earlier lectures, which seems ages ago, but it's only like 2 days ago, I guess. So it is a nice transport equation, but it does not satisfy our assumptions, T1, T2, T3, T4. So in particular, T4 was broken, and T3 I was not happy because this restricted operator turned out to be the zero operator, and it doesn't give us any information to work with. So maybe I just write down T4 is violated. So we need to modify our methods. And the key idea is actually, yeah, the key idea are 3 ideas. So I would like to discuss 3 ideas now, which is the moment closure, the hyperbolic scaling, the parabolic scaling, where the first 2 I only sketch, but the last one I do in detail, because the parabolic scaling we have seen in the first case, and now we see it again, and then I can show you the differences, what kind of differences arise. So, how do I do this? Oh yeah, let's move this guy up. And this. So then from here I make 3 arrows. One goes here, and this will be the moment closure. And then I do an arrow down here, which will be the hyperbolic scaling. And then I make an arrow over here, which will be the parabolic. So I'm not sure if this works with the arrangement of my board. So maybe this arrow should go here as well, so that it fits better. So there's a kinetic model. So hold on. So for the moment closure, this is basically exactly what Dr. Choi was talking about earlier this morning when he considered the Boltzmann equation. So that for the Boltzmann equation, you look then at the total mass, at the flux velocity, at the energy, and derive equations for those. And this can be done in this context too, but we have to be careful with the meaning. So what is the meaning of an energy if you have actively moving wolf, for example, or actively moving cancer cells? So let me give you a few details about this. So moment closure. So what you do is you define mass density P bar of x and t, which is integral P of txv dv. Actually, I defined it over there already. A momentum, which is P bar of xt times u of xt, where u is the velocity. And then this is integral v P of txv dv. And here you can see why it's called moment approach, because this is the first moment, the first velocity moment of P. Okay? And then an internal energy which is I denote by E of x and t, which is the integral of v minus u absolute value square P of txv dv. Okay, and then we also need higher order moments, but I'm not writing them down for now. So let's start with those. So what I then like to have is a differential equation for the mass density Pt. And so how do I get an equation for P bar? Well, I integrate the transport equation. So I go here, I integrate this thing, and then I get actually I get a conservation law for P. So maybe we can write this down. So this is plus gradient P bar u is 0. So maybe allow me to do this, to just write it down. I mean, you can sit down yourself and figure it out. That this, in particular, if you integrate the right-hand side, this integrates to 0. So then you get only this term. Okay. And then we want an equation for the momentum. So we multiply the transport equation by v, and then we integrate. And so then what we get is P bar u t equals, no, let's write it plus gradient of P bar u transposed equals minus gradient of P bar, and then the variance of q plus mu P bar expectation of q minus P bar u. So you will see very quickly why the moment method is not my favorite method, because it gets very, very complicated. And to do everything in glory details, I would need another 6 lectures, which you didn't give me. Or maybe we do a bit longer on Friday. So then, so I give a 6-hour marathon lecture. So, but at least let me explain the terms which arise here. So here we get the expectation of q, which is just integral v times q of xv dv, and we get the variance, which is integral v minus expectation v minus expectation transposed q xv dv. So then you see also that the expectation is a vector, okay, and the variance is the full variance covariance matrix. So again, some matrix arises like we had before in the diffusion limit. So and these all arise here. So here we get the diffusion matrix. Here we get the variance matrix, and here we get the expectation of q. And then we can do the similar thing for the energy. And this equation is even worse, but since I started, I just write it down. So this would be a gradient of EU equals minus nabla p bar, and then we get a tq, which is a third order moment, minus 2 nabla times u times p bar vq plus mu trace of vq plus eq square minus minus e, the original e, and then closing bracket, and then the third moment is integral v square v q of xv dv. So really, if you maybe have a graduate student which you really don't like, then let them work all this out. And they're busy for a while. Okay. What I would like to show you, though, is that you get higher moments arising. So if you look at the mass density, you get the first moment, pu. And if you do the equation for the first moment, you get the second moment here, okay, or here. And then if you look for the energy, you get even the third moment of q in here. And so then you can imagine if you do higher moments and higher moments, you get even higher moments arising in the equation. And that's called a moment closure problem. So at some point you would like to stop. And you would say, well, I only do the first 3 and then I stop. But the question is how to stop. And what people often do is, for the higher moments, they use the equilibrium distribution, or the Maxwellian, which you mentioned in your talk also. Let's see, how do I want to do this? What I want to do is called fast momentum relaxation. Fast momentum relaxation. Which is basically, I assume that the momentum equation is in quasi-equilibrium. I assume that is in quasi-equilibrium. So momentum equation is in quasi-equilibrium. Okay. And what that happens is really funny. So then many of the complicated terms disappear, and you can sub it in and sub it in and sub it in, etc. And again, a short step and just give you the result. So what you get out of this is then p bar t plus gradient of eq p bar equals 1 over mu nabla of vq p bar. Yeah. So this is an advection diffusion equation. So all of a sudden it became really handy. It's an advection diffusion equation. The advection term is given by the expected direction of the network Q, and the diffusion is given by the variance-covariance matrix of the underlying network Q. Again, it is anisotropic. So here we have the full second derivative of this matrix. So it has the same form as we had it before. Yeah, but now these terms EQ and VQ, they are given by the underlying network. They're given by the seismic lines, or they're given by the white matter tracks, depending what you're looking for. Okay. So let's do the same thing for the hyperbolic scaling. Where is that? Here. So in the hyperbolic scaling, I rescale space and time with a common factor epsilon. So sigma is epsilon t, xi is epsilon x. So maybe put it out here. And then we get a rescale transport equation, epsilon p sigma plus epsilon v times gradient p is LP. And then we do something which is called a Chapman-Enskog expansion in this context. Which is P is equal to P bar times Q plus epsilon times P orthogonal. Now I missed a... yeah, I can mention that later. No, I mentioned that now. So we expand P in a leading order term which is proportional to Q. Q is the network, the external environment, and then a smaller term which is perpendicular to Q. So here it shows already the setup which we are looking for. So earlier we split up L2 into 1 plus 1 orthogonal. Now we split it up into Q plus Q orthogonal. So this will be our setup also for the parabolic scaling, which I do next. And this basically summarizes the main difference between the earlier approach and this approach. So the split of the L2 space will be done according to the environment, according to the external network Q. And why? Why is it so? This is so because the kernel of L is Q. Yeah. So what is the kernel of the operator L? Yeah, let's compute this. So when is L P equal to 0? So this is minus mu P plus mu P bar times Q. Okay, so then I can solve this for P, and I get P is equal to P bar of xt times Q of xv. So meaning that as a V dependence, the V dependence is given by Q. So as an element in L2 space velocity, this is in direction of Q. So the kernel is a span of Q. Okay? And so the argument goes the other way. So it's because the kernel of L is this vector Q, that is the reason why we split the space according to Q and Q orthogonal. And so that's the rule. So this you can apply always. So in the Boltzmann case, for example, the kernel of the Boltzmann operator is 5-dimensional, which is mass, momentum, and energy. And then you split your corresponding function space into mass, momentum, energy, and then the orthogonal complement to all those. Okay. So, good. So then, and so this is the reason why I split it up like this. So I have a leading order term in direction Q, and then I have an orthogonal complement. And then I sub it into the expansion, and then I do leading order, etc. And I'll just show you what we get. So leading order here is P bar sigma plus gradient or divergence of EQ P bar is 0. So we get a pure drift equation. It's a hyperbolic limit, so we should expect a pure drift equation. But it's the same drift term as we had here. Right? These are the first two terms from this side, which also arise in that scaling. So it's kind of consistent. It works really nicely. So now on this side, the parabolic scaling. So here we scale tau is epsilon squared t. Xi is epsilon x, and we have epsilon square p tau plus epsilon v times gradient p is LP. Yeah, now this is a case we have seen earlier, actually yesterday, and so we do an expansion again. P is p0 plus epsilon p1 plus epsilon square p2, etc. And indeed, I go through these cases again, because here the detail shows up, and yeah, and I think that's important. One more thing. So we do this on L2 Q inverse V. So now instead of using the L2 space, I use a weighted L2 space, and the weight is 1 over Q. Okay. So now here, this does not work if Q is just a measure. So for this to work, Q has to be a smooth function. Okay, so for here we need to assume Q is smooth. So then let's look at epsilon to the 0. The leading order term, again, here is nothing, here is nothing. So we get 0 is LP. So meaning that P must be in the kernel, meaning that P is proportional to Q. So P0. So then P0, the leading order term is P bar of xt, Q of xv. That's the same as before. Epsilon 1. So then we have the P0 term from here. V times gradient P0 is L of P1. And same idea, we'd like to invert L. But to do this, we need a solvability condition. So we need to make sure that this guy is perpendicular to Q. So here the solvability means V times gradient P0 is in Q orthogonal, but orthogonal in this weighted L2 space. So let's write this out, what this means. So this means 0 has to be equal to integral V times gradient P0. Has to be orthogonal to Q, but then we use the weight dV divided by Q. And now you can see why I do this, so that the Q's have the chance to cancel. And then I get basically the same as I had before. So then this is integral V times gradient of, now P0 is P bar times Q dV. And I can take the gradient to the front. And this is, or actually divergence V Q of x and V dV times P bar of x and t. Like this. Okay, so now this integral term we know already. We have seen it before. So this guy is the expectation. This is EQ. Shows up again. But we want this to be 0, so we require that the expectation is 0. So, assumption. Yeah, so if the expectation is non-zero, then we have to do, well, then we have to stop. So then this scaling doesn't work, and we have to maybe use that scaling there. So I assume EQ is 0 for the following. Then epsilon square. So then we get the 0 order term for the time derivative, and we get the first order term P1 here, and then we get LP2. Oh yeah, and I forgot to compute P1. Let's go back to the epsilon 1 case. So now the solvability condition is satisfied. I can invert L. It turns out the inverse is again minus 1 over mu as a multiplication. So still part of this bit here is P1 turns out to be minus 1 over mu V times gradient P0. Okay. Yeah, then we have this. So now we integrate this equation. If I integrate the right-hand side, if I integrate this L, it always integrates to 0. We have seen this several times already. But you can do that in your mind. The reason is because Q integrates to 1. So if you write an integral over the L term, it is 0. And then this integral V P0 tau plus V times nabla, and then P1 is minus 1 over mu V times nabla P0, and then dV. Okay. And then again, the interesting part will be to figure out what this V times nabla times V times nabla, etc., what this term really is. So this is P0 bar, comma t, minus 1 over mu, And I can write this as V times nabla times V, applied to P bar times Q dV. So I just rearrange the terms just a little bit, but now I write it down component-wise. So this is P0 tau bar minus 1 over mu integral VI delta I delta J Vj of hold on, so I have of Q xv dv times P bar of xt. So first of all, I write these vector products in components, and I use summation convention. The Q has to stay inside the integration of V because it depends on V. The P bar does not depend on velocity, so I can take it out. But I should remember that the derivatives also act on P bar. Okay, but the derivatives don't act on V, so I can take them out to the front. This one and this one. Epsilon. So then this is P0 tau bar minus 1 over mu delta I delta J of integral VI Vj Q of xv dv times P bar of xt. And then maybe put a bracket here to really show that the derivatives act on everything, not just on the integral. Yeah, but now we are almost done. So because this here is the variance covariance matrix. This is V times V transpose with Q integrated. So this guy is VQ. Okay, so what we get in this case then is P0 tau bar is 1 over mu, and then two derivatives of VQ P bar as a resulting equation. So, and now this is exactly the same as here. So this is exactly this term we got from the moment closure as well. So this is really cool. So the hyperbolic scaling gives us a drift term, the parabolic scaling gives us a diffusion term, and the moment closure gives us both terms together. Yeah.
In the
here?
In the computation, but in the first time,
yes.
It starts from 0 equal to something. So can you explain why the left-hand side is equal to 0?
This one here? Yeah, sure. So this is integral L P2 dv. So let's do that somewhere maybe here. So integral L P2 dv. This is integral of, what is this, minus mu P2 plus the integral of mu, what is it, P2 bar Q dv. Okay, so I just wrote down the two parts of L, and then this guy is minus mu P2 bar, and here the integration only works on Q, so it's Q of x and v, which integrates to 1. So then this term is plus mu P2 bar, and then together this is 0. So thank you for the question. Yeah, I think this is not so clear at once. So yeah, so that's why that term is 0. Yeah, so I think actually it is really worthwhile to work out all these three cases, because it nicely shows how this goes together. And this is usually not done together. So usually people who do math biology, they know the parabolic limit, and they do this. And then people who work in fluid dynamics, they know the hyperbolic limit, and they do that. Where is it? Where's my hyperbolic limit? Anyways, I'm lost. My hyperbolic limit disappeared. Anyways, and then people who come from Boltzmann equation and kinetic theory, they do this. But really, it's everything is very, very closely related. So it's really nice. All right. Further questions to this? Yeah.
Hyperbolic scaling, you do not use the asymptotic analysis like extensions of epsilon or something in the hyperbolic scaling?
Very good. I could. Yeah. I need to find my hyperbolic scaling again. Here it is. Yes, I have that too. So maybe I can write that down also. Since you are asking for it, what can go? This can go. So as you are suggesting, you can also then look at the higher order term here, this orthogonal complement term, and you can solve for this also and plug it in, and then you get a higher order correction term to this limit. So which looks like follows. So this is P sigma bar plus gradient of EQ P bar is epsilon divided by mu. So the correction term now depends on epsilon because it's a correction term. Derivative of derivative VQP. So this is in fact as it should be. But then we get another correction term which is EQ times divergence of EQ times P bar, and that's it. Yeah. So we get those two terms. These are the two terms we would like to have, but we also get another correction term, which looks like from a Navier-Stokes equation. So it's kind of a transport of the expectation by the flow of the expectation itself. Yeah. So this shows up. I usually try to make sense in biological terms from whatever I do. So for this term, I didn't have a good idea what it means biologically. So if anybody of you has a good idea what this could mean, you can tell me. In the other scalings, it does not show up, but in this scaling, it does show up. Yeah. Other questions about this?
Which one is correct?
Which one is correct? No, if you go through all these things in details, you know exactly what assumptions you make. So for example, the parabolic scaling, I made the assumption that the expectation is 0. So in this case, this is a favorite method. This is the best method. If the expectation is non-zero, then you have to look at the relative size. So then if the expectation is large, then you would use the hyperbolic scaling here. And if the expectation and the variance are of the same size, you would use a moment closure there. So you do know what assumptions go into all this. Okay. Any other questions? Otherwise, I would like to show you for the last few minutes this in action. And let's look at some pretty pictures here. So down. On. All right, so here is already promised a brain image, and where it's yellow and red, these are the white matter tracks, and where it's blue or dark blue, this is where the gray matter is. So it's a very fine structure. I'm sure you have seen those kind of pictures before. This is called a fractional anisotropy map. So it shows us how anisotropic a certain region in the brain is. But the real brain tumor problem I discuss tomorrow in my tomorrow's lecture. Here I just like to show two made-up examples for the method. So here's a procedure again. So we have a drift diffusion equation. Now I call the drift term UC and the diffusion term D. But we have a directional distribution Q, and here I allow it to change with time as well. So if you do maybe surgery in the brain, then you can maybe change that. And then the drift velocity is the expectation, the diffusion term is the variance covariance matrix, And so when we have Q, we can compute these guys, and then we use the drift diffusion model to solve our problem. So what do we use for Q? Well, a good candidate is the von Mises distribution. And this is something I like to introduce now. So let gamma be any direction, a given direction. The von Mises distribution is defined by this formula here. And I should show you the distribution right there. So I0 is a Bessel function, modified Bessel function of zero order. And K of x is the concentration parameter. And the distribution looks like this. It is a normal distribution wrapped around a circle. That's what it is. And the direction gamma is this one where the maximum is, and otherwise it goes down and wraps around and lives on the circle. Okay? If the concentration parameter goes to 0, then this becomes the uniform distribution. And if the concentration parameter goes to infinity, then we get a delta distribution sitting on the direction gamma. So these are called circular distributions because they go about directions. So let's, so recall we have to compute the moments of the von Mises distribution. And this can be done, and they are known. And so using velocity space S times S1, then these are the moments. So I1, I2, I0, these are all modified Bessel functions. But then important is the drift is in direction gamma, which is the given vector, the dominant direction. The diffusion term has an isotropic part, which is the identity matrix, and a directed part, which is the dyadic matrix of gamma and gamma transposed. And this is also very interesting, so that we have these two components. Okay, so now we know what these guys are. We can plug them into the advection diffusion equation and solve it. So here's an example. I look at the fiber orientation in the diagonal. So they all point to the upper right diagonal. In the middle, it is very anisotropic. You have long arrows. In the outside, it is very isotropic. So in the middle, for example, you have this distribution. You can also write the von Mises distribution between 0 and 2 pi. So then you have a maximum in the diagonal. Otherwise, you go down. If you go further out, you still have a maximum, but less pronounced. And then if you're on the very outside, you have a uniform distribution. So now we are interested in the diffusion advection process on this kind of a setup. So what do we expect? So what do we expect? We kind of expect everything is transported up here, but then over here it is more like uniform diffusion. So we expect this. So here's the result. On the left, you get a hole or a low concentration here. It's all transported to the upper right, and you get a maximum here. But then this is a steady state picture. So then you get a uniform or more flat distribution surrounding it. So this shows many things. First of all, it shows that this thing doesn't have a maximum principle, because you get a maximum here and you get a minimum here out of a constant initial condition. And it does what you would kind of expect it to do, right? There is some net transport into the diagonal direction as well. Now, another interesting thing here is this picture is actually the transport equation. It's the transport equation with S is 10 and mu is 100. And this is the parabolic limit. And you see virtually no difference. So this also shows you how powerful the parabolic limit method is if the scaling is appropriate. So speed is relatively high, turning rate is relatively high. In this limit, you virtually get the same results. And now you can imagine that solving the parabolic limit is much easier. So this one is actually this here. It's much easier than solving the transport equation with all these v's and all these directions. Okay. Let's look at another similar example, which is the bimodal von Mises distribution. So now we have two directions. We have gamma and we have minus gamma. And we have a normal distribution sitting over both of them. And so you get a plus gamma term here and a minus gamma term there. And then you can again compute the macroscopic constants. Now the expectation or the drift velocity is 0. And the diffusion coefficient has an isotropic and an anisotropic part. Similar setup. So now we look at anisotropy in diagonal direction. but now it goes both ways, up or down. So there's no more preference of going up. Here's a distribution, which has 2 maxima now. And then what you get is maybe also what you expect. So it is driven in diagonal directions. You get 2 maxima here, and it's sucked in from the other diagonal, where you have 2 minima arising here. Okay, and then here we have shown the transition to the parabolic limit. We start with a low speed and low turning rate, then we increase the speed and turning rate, and then we increase speed and turning rate again. And going from here to here to here, we're getting closer and closer to the parabolic limit. Okay. So finally, and this is, then I finish with this one. This is a brand new result because we want to do this in 3 dimensions also. Now in 3 dimensions, the von Mises distribution has a different name. I don't know why the statisticians do that, but it's called the Fisher distribution. It is really the same function, only the normalization constant is different. You get a hyperbolic sign in here. But so now you have to consider it to be on the sphere, and you have a spherical distribution on the sphere. It's known as Fisher distribution. And actually, and now we need to compute the moments, first and second moment. And the second moment was unknown. We could not find the second moment for the 3-dimensional Fisher distribution anywhere. So we were able to do it ourselves. And this is here. So the expectation was known. There's a hyperbolic cotangent in here. But the variance was not known. This is a new formula which we just submitted this year. And in particular, if we do the brain modeling later, we need the 3-dimensional distribution because the brain is 3D. So we need this formula then for our brain studies. Yeah, and so then let me finish with this today, and then tomorrow I study really the applications to wolf and to brain. Thank you.